So this is going to be our second video on thermodynamics. And we're going to start out here by talking about the second law of thermodynamics. So this says that whenever a spontaneous event takes place in our universe, it is accompanied by an overall increase in entropy. Now, if you remember, when the previous video, we said entropy, in a word, entropy is disorder. Okay, so sometimes the second law is stated this way, and that is the entropy of the universe is constantly increasing. In other words, things are slowly degenerating. The universe is just slowly degenerating into a more and more disordered state. Now, in the previous video, I mentioned two reactions or processes that are endothermic, and yet they still happen spontaneously. Okay, so for example, one of which is the evaporation of water. You leave water out, it will slowly evaporate, even at room temperature. Same thing, dissolving of potassium chloride. You dissolve up potassium chloride and water, solution gets cold. It's taking in heat because it's an endothermic reaction. Well, what do both of these reactions have in common? They're both going to higher entropy. Okay, they're both going to higher entropy. The first reaction is going to higher entropy, right? Because we're going to liquid to gas. That obviously leads to a big increase in entropy. And then the second one is the dissolving of a solid. So remember what I said, in a solid you've got all the ions are packed into a nice lattice. The lattice is orderly. That's a highly ordered state. When it dissolves up, it sort of breaks apart and you have these free-floating ions in solution. Well, that's more disordered. All right. So any event that is accompanied by an increase in entropy of the system tends to occur spontaneously. We can state that another way, or perhaps a better way to say it, is that an increase in entropy is one of your driving forces for a reaction. See, there's two driving forces. Reactions happen for two reasons. They're going to lower energy or they're going to higher entropy. But neither in itself is an absolute predictor as to whether a reaction will occur spontaneously. So the sign of delta S, yes, there's this driving force toward, it's one of your driving forces to go to lower, for a reaction to want to go to lower entropy. But this alone can't be used to predict the spontaneity of a reaction. So energy by itself, or neither energy by itself nor entropy by itself, can be used to predict the spontaneity of a reaction. Okay? This leads us to the third law of thermodynamics, which says that at absolute zero, the entropy of a perfectly ordered, pure crystalline substance is zero. So, unlike energy, the total entropy of a system can be known. So remember what we said about energy. Back to my example of the coffee, the hot cup of coffee. We said only changes in energy can be measured. We can measure the change in energy as the coffee cools off, but we can't know how much energy it had to start out with. This is not true. This is not true of thermodynamics, or I'm sorry, this is not true of entropy, because we have a definition for zero entropy. Okay, at absolute zero, entropy of a perfectly ordered, pure crystalline substance is zero. Okay, so one more time, this means that we can define zero entropy. All right, so you can look in your book and you will see standard values for entropy. You won't see energy values. But you will see entropy values. So the standard entropy is defined as the entropy of a substance at 298 Kelvin and 1 atmosphere of pressure, right? So anytime you see this superscript, That means standard conditions. That means 298 Kelvin and 1 atmosphere of pressure. And like I said previously, anytime you measure a change, it's always final minus initial or products minus reactants, right? So we can look up for a reaction, we can look up entropy values and then calculate the calculate the entropy change for a reaction, right? So that's what we're going to do in this next example. So we're going to react ethylene, which is C2H4, with hydrogen to form ethane, which is C2H6. Now, before we even get into the calculations, I want you to look at this reaction and tell me, is it going to higher entropy or lower entropy? Okay, well, let's look at what we got here. It's all gases. It's all gases, so there's nothing to do with phase changes here. But we've got 2 moles of gas on the left and only 1 mole of gas on the right. So the number of molecules is decreasing. So this is a case of the molecular complexity. We're going to increasing molecular complexity. We're making a big molecule out of 2 small ones, right? So the entropy should be decreasing. So let's look up some of these values for ethane. It's 229.5 joules per Kelvin mole. And by the way, that's your unit on entropy, joules per Kelvin mole. Okay. For hydrogen, it's 130.6. And for ethylene, it's 219.8. Right? So to measure a change, it's going to be products minus reactants. So C2H6 said was 229.5 minus the sum of these two. So the sum of 130.6 and 219.8. And what do you get? Minus 120.9 joules per Kelvin mole, which is negative, which is what we predicted at the start by looking at the reaction, correct? This is going to lower entropy. In other words, it's becoming less disordered, it's becoming more ordered, actually, by the reaction happening. So this leads us to Gibbs free energy. Okay, so we said that enthalpy, which is delta H, cannot be used as the absolute predictor of a reaction, and neither can entropy, which is delta S. But the Gibbs free energy combines these into one expression. Okay, so that's the Gibbs free energy. And so this can be used as an absolute predictor as to whether a reaction will occur spontaneously or not. Remember I said the 2 driving forces for a reaction, lower energy or entropy or higher entropy. And this ties them into one equation. So a chemical change can only be spontaneous if it is accompanied by a decrease in free energy of the system. In other words, only if delta G is negative. Okay? Delta G is negative, the reaction is not going to be spontaneous. I'm sorry, if delta G is negative, the reaction will be spontaneous. If it's not negative, it will not be spontaneous. Okay? Which leads us to the idea then that depending upon the signs of the enthalpy change and the entropy change, we're going to have 4 possible cases. Okay? So our first case is if delta H is negative and delta S is positive. So let's think about this for a minute. If delta H is negative, right, that means the reaction is exothermic. That means it's giving off heat. And that's basically one of the driving forces for a reaction. And if delta S is positive, that means it's it's going to more disorder. It means then it's energy driven as well as entropy driven. In other words, if you look at our sign, if delta G is delta H minus T delta S, if delta H is negative, if this is negative, okay, and delta S is positive, you're subtracting delta S. So this component is negative, and this component is negative. So guess what? Delta G is always going to be negative, no matter what the temperature is. So in other words, we can say that a reaction like this, we can say that it's both energy driven and it's entropy driven. It's going to lower energy, and it's going to higher entropy. It's going to be spontaneous all the time, okay, at any temperature. Now, if we look at the reverse of this process, if delta H is positive and delta S is negative, delta H is positive, that means we're dealing with an endothermic reaction. And if delta S is negative, that means it's going to less entropy. So it's neither energy driven nor entropy driven. So if delta G is delta H minus T delta S, this is the opposite case of the first one. If this is positive and this is negative, subtracting the negative makes this component positive. So delta G is always going to be positive. Can never be negative, right? So the reaction is non-spontaneous at all temperatures. So we can say that it is neither energy driven nor entropy driven. Okay. So if we look at a reaction, third case is where delta H is positive, right? So we're dealing with endothermic here, but delta S is positive. Okay, so it's not energy driven, but it is entropy driven, right? So if we look at, again, let's look at the signs. Delta G is delta H minus T delta S. Now, this part is positive. So it's not energy driven. It's an endothermic reaction. But the question is, can this part outweigh this part? Okay. So you're subtracting T delta S. If delta S is positive, but you're subtracting the positive, which makes it negative, or makes it delta G more negative, right? So the bigger T becomes, the more negative delta G becomes. Right, so we say that this reaction is spontaneous at high temperatures. So remember what we said about entropy. The entropy increases with increasing temperature. Right, so as we increase the temperature, the entropy component of this equation increases and delta G becomes more negative. Okay. In our last case is if delta H is negative but delta S is positive. And you should be able to figure this out at this point. If delta H is negative, so here we have an exothermic reaction. This is energy driven, but it's not entropy driven because we're subtracting the negative. And so this part is actually going to be positive. Negative times a negative is a positive. So as the temperature increases, delta G becomes more positive. So this reaction is spontaneous only at low temperatures. So if T is small, if T is low, delta G can still be negative. Okay, but as temperature increases, this is going to become more positive, and at some temperature, then delta G will become positive. So one more time now. So this is energy driven, but it's not entropy driven. Okay. Let's look at an example. Suppose we look at this reaction. Phosphorus pentachloride is breaking down into phosphorus trichloride and chlorine gas. Okay, so let's look at this reaction. Again, before we even delve into this, can you look at this reaction and predict the sign of the entropy change? Right, it's all gases, so don't have to worry about solid, liquid, gas. So we just look at the number of molecules. We have 1 here, 2 here. Right, we're breaking a big molecule down into 2 small molecules, right? So that's going to be an increase in entropy, because anytime we make small molecules out of the big one, entropy is going to increase. So suppose we look at some data. All right, so for this reaction, we suppose we look up for the reaction, or we calculate it, that delta H is 92.5 kilojoules per mole, and delta S is 182 joules per Kelvin mole. Okay, so the first thing we want to do is we want to calculate delta G at 25 degrees Celsius. Okay, so 25 Celsius is the conditions under which these were measured. These are standard conditions. So is this reaction spontaneous at standard conditions? So we're going to have to be consistent with, you're going to have to be careful with your units here, because this is kilojoules and this is joules. Okay, so this is kilojoules and this is joules. So to be consistent with the units, we're going to have to multiply this one by 1,000 to convert kilojoules into joules. Okay, so we're going to say delta G is delta H minus T delta S. That's 92,500 joules per mole minus 298 times 182 joules per Kelvin mole. 298 Kelvin times 182 joules per Kelvin mole. And notice the kelvins will cancel, and that's going to give us joules per mole. Okay, so that's 92,500 minus 54,236 joules per mole. That comes out to be positive 38,246 joules per mole. So is this reaction spontaneous at 25 Celsius? And of course the answer should be no. And why is that? Because delta G is positive. The reaction is going to be spontaneous. Delta G has to be negative. Okay, so the last question we're going to ask here is, at what temperature will this reaction become spontaneous? In other words, this is one of those cases where delta G will become negative as we increase the temperature, right? So because delta S is positive, we're subtracting T delta S. So as the temperature increases, delta G becomes negative. So what we want to know is, okay, suppose we're running this as an industrial process, how hot, what temperature are we going to have to achieve for this reaction to happen? So if delta G is 0, then you can rearrange the equation and say T is delta H over delta S, right? In other words, if delta G is delta H minus T delta S, right? Well, if delta G is 0, then we can say that delta H, and move the T delta S over to the other side, so that delta H is equal to T delta S, or then T is delta H over delta S. Okay, So 92,500 joules per mole divided by 182 joules per Kelvin mole, right? And the joules and the moles will cancel, will give us Kelvin, okay? And this comes out to be 508 Kelvin. We subtract 273 from it to convert it into Celsius, which is 235 Celsius. So this is basically your break-even point. So at this point, at 235 Celsius, delta G is 0. So think of that as your break-even point. So basically, any temperature over 235 Celsius, the reaction will be spontaneous. All right, so we will stop here for our second video.